test.
Okay,
You
yeah.
haven't tested it.
Huh?
You haven't tested it.
Yeah.
No.
That's right.
I'm leaving. You're voting him off the island? Try this.
No, but test next class period for sure.
Yes.
We just won't be a part of that for sure.
So, are there any questions on the homework? All right, remember those are all due, and the quiz number 1 for chapter 2 is also due. All right, so
When is the quiz due? Like,
oops.
11:59.
They're all due the day of the exam at the start of class.
okay.
Just because I know some people like to do it right before class too, so. Ideally, you've done most of these, and you can save the quiz as like a gauge on where you're at, and then go back and review some of your homework questions, or even the exam 1 review, just more practice problems. You could try that as well. All right, so we left off with the intermediate value theorem in 2.6. This is the last thing we're discussing in 2.6, but since it deals with continuity, a lot of theorems deal with continuity, but this is one of the things we're going to look at as an implication of continuity as well. And so what we said is, if more or less, if we know that in between 2 x values the function is continuous, then we know that in between those values it takes on all values, is basically what that's saying. And what we said was that, 1, it doesn't tell us what that particular value is when we find this c. And 2, if it's inconclusive, then we can't say that there is no c. There might be a c, there might not be a c. Okay. The other implication of the theorem is that sometimes when you're asked to solve a particular equation, you might remember some of those you solved took a little bit of time, but then you come up with the fact that there is no solution. It seemed like a grand waste of time to spend 5 minutes on a problem that didn't have a solution, right? So this could tell us if there is a solution. So if we're given a specific equation to solve, we could apply the mean value theorem to determine if there is even a solution. Again, the theorem won't tell us the solution, but at least we know, hey, there's a solution. Maybe I can solve this algebraically. Okay. So I'll write that here as well. The intermediate value theorem will also tell us if we'll just say an equation has a solution. But, as we noted in bullet 1, it does not tell us what the solution is. Does anyone have any questions on this? We're going to look at one example and then conclude 2.6. Okay. So our example, let's take so our instructions use the intermediate value theorem. To show there is a solution to the function is 4x cubed minus 6x squared plus 3x minus 2 equals 0 on the interval from 1 to 2. So the idea, particularly when we use the intermediate value theorem, is that we're given some sort of equation on a specified interval. And so it's asking, does this function ever equal 0 in this interval? And what we're looking for is basically a yes or a no. Again, this theorem won't tell us if there is a solution, where it's at. It could be, it could be at 1, it could be at, 1.5, it could be at 1.736. It won't tell us where it's at, it just will tell us that there is or is not. Okay, so let's go back up to the theorem, and it says, suppose that f is continuous on the interval, the closed interval AB. So that's really the first thing you want to think about. If I'm about to use this theorem, I have to determine, is that particular function of x or t or whatever, is that continuous on the specified interval they've given me? So let's just call this, since all of our x's are over here, let's just call this f of x. And note, we could rearrange this as well. So, or it could be presented as 4x cubed minus 6x squared plus 3x. Does that equal to 2 on 1, 2? So there's various ways we could write those things. And if that were the case, then we would just call this thing f of x. Just make sure that whatever you're labeling as f of x, or g of x, or h of t, you have all of the variables on that one particular side. Because the theorem doesn't, go back to the theorem doesn't have us equating a function of x to another function of x, right? So it's just all the variables to one side, that's going to be our function. And then whatever number is left over here, that's going to be that particular L that's expressed in that theorem. And here's our A and our B. So the intent isn't for that not to be confusing, just to show you that it can vary how they write the expression out and say, is there a solution to this equals to that on this interval? The main thing you want to remember is to put the variables on one side. Whether you equate it to 0 or 2 or negative 37, whatever the problem has in there, it doesn't matter. All right, do y'all have any questions about that? So I'm going to erase this second line here, just because, well, I don't know, just for consistency, just to work with one of these but not both. It doesn't matter which one you work with. I typically gravitate towards setting the function equal to 0. That way we can, when we compare the y values, it'll be clear, a little bit clearer, I think. So this is, I'm going to erase this. Does everybody have that, if they want it in their notes? So the first thing we really need to address and state somehow, I don't expect you to recall specific formulas or theorems or definitions or anything like that, but we do need to justify, if we're going to continue with this theorem, we do need to justify that this function is continuous on the given interval. So however you justify that, it just needs to be clear. Don't just jump right into computing values, because the underlying assumption to use this theorem is that the function is continuous. Okay? So the first thing we're going to address is f of x continuous on 1, 2. So if you reference the theorem, that is the first sentence of that theorem. Assume f of x is continuous on the closed interval AB. Yeah?
So why is it the closed interval in the first step, but an open interval in the problem?
Okay, so we noticed in this theorem that we have the function needs to be continuous on the closed interval, and L is, then the conclusion is that there exists at least one number in the open interval AB. Okay, so the reason that could happen, or the reason they're stating it that way, is because if, let's say we evaluate our function here, f of x, at 1 or at 2 at the endpoints, and if they equal to our L, if f of 1, for instance, was 0 or f of 2 is equal to 0, then there really wouldn't be anything to do, right? We would automatically know that there has to be a solution in that. So it's a little bit more of a loose restriction here with an open interval than with a closed interval. So it's just to kind of cover more ground, I guess. Okay. So is f of x continuous on the interval 1, 2?
Yep.
Yeah, how do we know?
Because it's a polynomial.
Because f of x is a polynomial function, and polynomial functions are continuous where?
Everywhere. Well, on their entire domain.
Over their entire domains.
On their domain, which is all real numbers. So that's really all we need to remember to justify this is continuous. So yes, we'll say yes. Since f of x is a polynomial, it is continuous. It is continuous on its domain, negative infinity to infinity, and therefore it's certainly continuous on, they call that a subset of its domain. So it's continuous on its domain, and therefore continuous on 1, 2.
What was the other thing stuff next to continuous if it's rational function?
So yeah, then this is kind of where we have to remember domains of functions, right? Because if a square root function showed up here, then we would have to remember where is the square root function continuous?
From 0 to infinity.
Yeah, so from 0 to infinity, including 0, so it's right continuous at 0. So that's where the domain aspect sort of comes in. If this were a rational function, then where are rational functions continuous?
Anywhere that doesn't make the denominator equal 0.
Right. Rational functions are continuous on their domains, except for you have to worry about with rational functions, when do I divide by 0? They can't be continuous where you divide by 0. So that idea of continuity and domain are basically the same, except for when you're dealing with a piecewise function. All right. So we addressed the assumption f of x is continuous. Then the next step is L, which is 0 for us. 0 is a number strictly between f of a and f of b. So we don't know what f of a and f of b are yet, but we have a and we have b and we have f of x. So the second step is to compute f of your endpoints. So second, compute f evaluated at the endpoints. of the given interval a and b. So we're going to compute f of 1, and we're computing f of 2. So we have to remember how we labeled our function f of x. We labeled it as 4x cubed minus 6x squared plus 3x minus 2. So we're plugging 1 and 2 into that function above. Okay. If you want to verify, f of 1 is negative 1, and f of 2 is equal to 12. So what is that? We know the function is continuous. We know f of 1 is negative 1 and f of 2 is 12. Then now what do we know? Right. The value L that we were checking for isn't 0 in between negative 1 and 12? Yeah. So that, I think it's, I don't know, it's a matter of how you look at it. But if you set your function to 0 and call that your L, if you get a positive and negative number, then it's 0's for sure in between positive and negative number. Okay. So, you know, if kind of wondering, well, what does that mean? Let's look at it graphically. Here's my closed interval from 1 to 2. And we know that the function evaluated at 1 is negative 1. And f of 2 is 12, so we'll just say that's up here. What we're trying to check for is, does that function ever equal 0? Is that function ever equal to 0? Well, we have 2 points that are above and below 0, but again, the continuity aspect of this is totally crucial, right? If I had a function that was doing this, then there would not be any x value that gives me a 0, right? It's only based off the fact that we know this point and that the function is continuous. So it doesn't really matter what the function's doing, right? We know it's not doing that because it's a polynomial, but the function could be doing whatever it wants to do in between those 2 points that we've computed. We just know that it's continuous, meaning it's all connected. So at a certain location, you know, let's say that's here, at a certain location it has to pass through 0. In other words, that function has to equal 0 somewhere in between somewhere in between 1 and 2. Does that make sense?
So we're just trying to find where C is 0.
Yeah, well, we're not trying to find where C is 0. What we're doing is this theorem just tells us that there is at least one of those locations. There's at least one x value we call C in the given interval, so that when we plug that x value into this particular function, it's going to equal 0. So let's...
It's just a quick way to kind of evaluate that original function without having to sit there and go through all the algebra.
Yeah, right.
Right, and it's essentially really all it's doing.
Yeah.
It's just, you know, saving time essentially.
So yeah, right, we know that there's a solution. This thing isn't going to tell us where the solution is, but then we know that there for sure is a solution in this interval. So I can then default to other methods and solve when does 4x cubed, etc. actually equal to 0.
Doing that's a heck of a lot quicker anyway than sitting there evaluating the true function.
Yeah, right. But so, like, you know, this is just a, you know, in one way this theorem is just a check. Does a solution exist? Yeah, a solution actually exists because what we'll say here is since, let's try to here, since L, which was 0, is in between f of 1, which was negative 1, and f of 2, which was 12. Since 0 is in between f of 1 and f of 2, there exists at least one so that's always the conclusion. There is at least one. If L is in between these two y values you computed, then there has to be at least one value in the interval that you've provided, or that was provided, so that the function evaluated at C is equal to L, or in our case, f of C equals to 0. That's it. That's as far as we go with that. So it doesn't really, it kind of narrows it down because we know there's a solution in the window from 1 to 2, but there's infinitely many numbers in between 1 and 2. So it really doesn't help as far as determining the solution. There's still an infinite amount. At least we know the solution is one solution is in between 1 and 2. If we wanted to sort of use this theorem to try to get a better representation of where that solution is, then what could we do? Like if I wanted to find, if I wanted something a little bit more definitive besides the interval from 1 to 2, where my solution could be, what could I do with this theorem?
You plug 0 in?
Well, if we plug 0 in, we're finding out when our y-intercept, when x is 0, that would just give us the function's location on the y-axis.
Could you just restrict the subset of the domain you're working on? Like instead of going from 1 to 2, go from like 1.5, go from like 1.5 to something smaller?
Right,
Like,
yeah. We
just
could...
a smaller subset?
Yeah, exactly, yeah. We could just take that interval and make it smaller and say, well, is there a solution from 1.5 to 2? We say, yeah, there is a solution from 1.5 to 2. And we could say, well, is there a solution from 1.9 to 2? Maybe there's a solution from 1.9 to 2. So you could sort of like close in on that solution, but it would involve making the interval kind of shrink around where you think that solution might be. And we'll look at the graph as well to verify. I mean, the idea is that we don't need the graph because it's just as simple as evaluating two y values and determining if the y value in the problem is in between the two y values you've computed. And again, the most important thing is that the function is continuous. Okay, so there's our function. We see that there's a solution where the function equals to 0. And we certainly see that in between 1 and 2. We'll zoom in on that. But notice the theorem didn't tell us that the solution is 1.221. So that's just verification that what we did was actually true. So there's 1 and there's 2. Like this. Just for reference. All right, any questions on that? just so you're fully aware, the question could also be presented as the following. So it could have asked, when does 4x cubed minus 2 equal 6x squared minus 3x? Or does this function equal to this function on 1, 2? So sometimes they like to mix stuff up. It's not always going to be on one side. So if you see one worded like this, really the most important thing is that you're placing all of your variables on one side. That's your f of x from that theorem. If you want to consider 2 as part of the function, that's fine, but for sure every variable needs to be considered part of that function. Or like we wrote originally but erased, or as we were given in the original problem. So either way, this would be our L, this would be our L, depending on how you rewrote it. And then these are our functions. So again, you could work with either or, but you definitely wouldn't work with the first way it was presented to you. So are there any questions on 2.6? Yeah.
How would we solve this differently if we set it equal to 2 versus how we just did it?
So how would we look at this or solve this differently if we looked at it L as 2 instead of L as 0?
2 is still in between -1 and 12.
Right.
Yeah, you do it the exact same way.
Yeah, you do it
What you
the
said.
exact same way. Because notice if our L is 2, the f evaluated at our endpoints doesn't change. The only thing we would look for then is 2 in between -1 and 12. And we would say, since 2 is in between f of 1 and f of 2, then there's a location where that function is equal to 2. Yeah.
Wouldn't you have to evaluate the function differently because doesn't 2 go away because it's the value that you're like looking for?
Yeah, so in this particular instance, 2 is an endpoint. So if we evaluate if we evaluate f of 2, then let's go back up. Well,
We're not.
yeah, let's go back one page. So it just says if L is in between f of A and f of B, it doesn't really account for the fact that what if L is A or L is equal to B. It doesn't really say anything about that. So
That wouldn't matter though, because L is a y value,
Right.
not an x value.
right, yeah. So if we evaluated f of 1 and f of 2, where we're using this one instead, then this is a y value. So it doesn't really matter that it's on the endpoint. But again, if it was an endpoint value, like if we plugged 2 as x into this function, then it would be immediately obvious, does that ever equal to 2? Is f of 2 equal to 2? Then we would say, yeah, well, it happens at the endpoint, as opposed to saying it happens somewhere in between those values. Does that help? Does that make sense? Okay. Yeah, any other questions? Yeah.
Wouldn't it change the value of our A and our B though? Because since you're moving it to the other side, we're no longer subtracting by 2.
Oh, right, yeah, yep. Yeah, totally good point. Very easily overlooked, as I just did. So notice if we're saying our L is 2, this now is our f of x.
It's now 1 and 14.
Yeah, so it's gonna be a different you're going to get a different value for this function evaluated at 1 and 2, as opposed to evaluating this function at 1 and 2. But the principle is the same, is that L is 2 in between the y values generated here at f of 1 and f of 2.
Yes.
Yeah, so is our L in between here somewhere? That's really all you're ever looking for. And the fact that the function's continuous.
So even though you may get different results, the statement is right?
Yeah.
Okay.
Even though you may get different results, it still just defaults to the fact that this y value is in between these two y values, and the function is continuous. So make sure if a question like this on the exam shows up, that you're somehow addressing the continuity aspect of the function that you're calling f of x. Because if you just go into computation, if you just start with this second step, you cannot make that conclusion unless something is said about continuity.
So let's say on an exam, it's not continuous, it's not a continuous function.
Mhm.
You just put like no, like it cannot be solved.
Yeah, so if the function is not continuous, then the very assumption of the theorem doesn't hold. So we can't conclude anything. So we would say it's inconclusive. There might be a solution, there might not be, but certainly since it's not continuous, this theorem does not apply.
In the past, we've just, for what I've done is we've just written the IVT will not work on this equation.
Yeah, so you could say it won't work. It's inconclusive. So yeah, particularly I think when it's more appropriate to say that the intermediate value theorem wouldn't apply, because that's the main assumption of the theorem.
Right.
But your function that's given to you on the exam would be continuous. I wouldn't try to throw a curveball in there. So you just need to be able to justify that it's continuous. You don't have to reference specific theorems or anything like that. I just need to see some reasoning, like how do you know that's continuous? You might know in your head, like, oh yeah, I can picture the graph in my head. If you can picture the graph in your head, then just write down the domain of the function. The function's domain is blah, blah, blah. Therefore, it's continuous on a smaller portion of its domain. Does that make sense? I know usually the domain is sort of fuzzy on certain types of functions, so that's why, again, you need to know the domain. All right, yeah, that's it. Other questions or comments on any of this? Okay. So in 2.7, we're going to look at the precise definition of a limit. I know this, before we actually look at the first page though, I do want to take a little bit of time to talk about something that we see showing up in the definition. As far as the notation goes, something you might have seen briefly and then sort of never again after that. So we'll and that has to do with the fact, or the statement, when we see the absolute value of x is less than some number. What we want to try to remember is how do we interpret that, or to write it in a slightly different way. The absolute value of x minus 0 is less than a number. So what do we know about that, or how do we interpret that graphically? Like, what does that mean?
It's a piece that falls between, like, say, x was 3. It's a piece that falls between -3 and 3.
Okay. So it's a piece that falls in between -3 and 3. For example, the absolute value of x is less than 3. Do y'all agree with that? So here's this value here, 0. So typically, I think when that's introduced, they say think of this particular absolute value as a distance from the origin, right? So if I had, like the absolute value of x was less than 12, then that says, well, I'm 12 units, I'm up to 12 units away from the origin in either direction, right? Distance to the left or distance to the right. Oops.
So that would also be its limit. Or no, because it's included.
Yeah, I guess it would have to be put into that context.
Right.
Yeah. Okay. So to, back up here to the more generic statement, and we'll see why we wrote x minus 0 in a minute. But the way we interpret this is just in words. I guess we can think of it as in units from 0 on the x-axis. So when we see a statement like the absolute value of x minus a is less than some number, and now sort of have a better interpretation of what that was. So our interpretation for the absolute value of x minus a is less than some number is what?
N units from A.
Your n units from a on the x-axis, right? Yeah, good. N units from a on the x-axis. So here's the x-axis, here's A. We are in units to the left of A. Or we're in units to the right of A. Is that minus A? So can you already see how this might be put into the context of a limit? And as far as the context of a limit goes, what has to happen to n if I'm approaching A? It gets smaller. Yeah, so we just make, when we look at the definition of the limit, we're just going to think of that number as a super small number. Like I'm 10 to the negative 32 from A. Okay. And we have a similar interpretation, or the same interpretation for the absolute value of f of x minus L is less than some other number. We'll say m. So what is that? How is that interpreted in words?
Probably in units from L.
Is
on the y-axis, right? Yep. So we're m units from L on the y-axis. So that inequality just represents any value, you know, as long as we're anywhere in here, if we're within that window, then that inequality with the absolute value is established or is true. So any of those green dots make that inequality true. All right, any questions on that? So hopefully now when we look at the definition of a limit, that it makes a little bit more sense. And this is the actual definition of a limit. Everything we said about a limit as far as looking at its definition, we had that parenthetical statement that said it was a preliminary definition. So, but this is the actual real definition of a limit. Okay, and it says assume that the function exists for all x values in some open interval. So we see that open interval here from -3 to 3, or we see that open interval from a minus n to a plus n. So assume that it's exists in some open interval containing a, except possibly at a. We say that the limit of f of x as x approaches L, written this way, which we're all accustomed to that notation by this point. So when we see that notation, what it means is if for any number we're going to call epsilon that's bigger than 0, there exists a corresponding number delta that's bigger than 0, such that we're epsilon units away from L on the y-axis whenever we're delta units from A on the x-axis. The only restriction is just think about epsilon and delta as very tiny numbers. The other way to read that is it says that this happens when this happens. So we can say that, you know, the absolute value of x minus a is less than delta, then the absolute value of f of x minus L will be less than epsilon. Remember, those things are determined, functions are determined by what's happening with x, not y. So we could read that if for any epsilon there is a corresponding delta such that when x minus a is less than delta, f of x minus L is less than epsilon. And so I think it's a little bit easier than to think about the images we drew as far as how do we interpret those two absolute value inequalities in words. If we go back and look at that, we can say, well, you know, this is our delta. It's a super small number. And what I'm saying is, if I'm within this window of A, then that's going to force f of x to be within some window of this number. Can I extend this page? So I don't know, whatever, we have some function f of x. Here's, let's say this is a. And the function could exist at a, it might not. So let's just say it does that at a. And then there's L. So it's what the definition is saying is, if I'm within this many units of A, then that's going to force my function to be within this many units of L. And it really does depend on the function, right? So I'm not trying to do that justice, but I don't think well,
This was not done.
No, epic fail. So I'll move that a little bit over, just so it's.
Bless you.
Thank you.
Just so we can try to get a picture of this. So I'll do a little bit more well-behaved here. If I want to be within that many units of A, then my function is going to be here. And here. Then I'm going to be within that many units of L. And so the idea is that there wasn't a restriction on how close I am to A other than the fact that it's not 0, right? It's just some small number that's larger than 0. So again, if I said, well, I want to be within that many units of A, then I have to be within this many, then that forces me to be that close or within that distance from L. And so that interval just keeps shrinking and shrinking and shrinking until we're, it's hard to visualize, like an interval right around a point, but that's kind of how you would imagine it, right? Imagine those parentheses like closing in on that point. But we know those parentheses is like, we're visualizing getting closer and closer to A by making that window smaller. But that's all that absolute value inequality statement means for both the X and the Y axis. Does anyone have any questions?
What was the equation associated with the graph you just drew
That was just one particular,
in general?
yeah, that was just let's visualize both of them, the definition of the limit put together, like for X and Y.
If we were asked a question on it, like how would the equation be set up?
Okay, so yeah, we'll look at an example. There's proofs, which we don't do, and then there's using graphs to answer the question about if epsilon is this, then what is delta? Okay, so for us in practice, we sort of work it we reverse engineer it to find delta. So we're given this epsilon, and we find delta. So that's how it shows up for us in practice. So we can come back to that first example. The next 7 are sort of short answer. We can come back to this if we need to, but I do want to at least address question 4, because it is directly related to the definition. So does the set, when we look at 0 is less than the absolute value of x minus a less than delta, does that include the point x equal to a? No, how come?
Because this is less than, or less than, not less than or equal to. That's.
So which one are you specifically referring to? This one right here or this one right here?
I think she means the left one.
One of them.
The left one because
One of them. Yeah.
It would be the one on the left because it says that it has to be greater than 0.
Right. So notice that this statement here says that distance that we are from A on the x-axis can't be 0. The only time x equals to a, if x were equal to a, what's our distance? 0. So no, if x equals to a, the absolute value of x minus x, thought I could correct that, but the absolute value of x minus a when a is x is identical to 0. But in our definition, it says that the absolute value of x minus a, we'll just look at that piece, not the delta part, but the absolute value of x minus a is strictly larger than 0. It can't be equal to 0.
So based off of that, can we say that just looking at the left side of that there, does that mean that x is in that situation, x also has to be greater than a?
Looking at the inequality we just wrote,
Or more so the ratio given in the example on 4, the 0 less than absolute value x minus a.
okay, yeah, so, well, the absolute value would take care of that. So like if x were larger than a, like if we had minus 4, minus 1, and that's still going to be negative, but the absolute value of that is positive. So that's still bigger than 0. Or if this were larger than a, I think was your question, it's still positive. But either way, the absolute value takes care of it for us. Whether this x value is larger than a or smaller than a doesn't matter, because we're just considering the distance or the magnitude. So, and in that case, that sort of gives us, that absolute value statement also gives us the ability to approach from the left and the right, because it's sort of simultaneous that we're doing this, right? So that's from the absolute value. Did that answer your question?
Yeah.
Okay. All right, so that's why when we looked at the preliminary definition of a limit, we said that, the function, let f of x be defined at all x values except for possibly at a, because even if your function's not defined at a, it doesn't matter. So like whatever our function is, let's say our function was that thing again. You got something weird going on. It doesn't matter because we're never going to get there, right? Like all of our x values, we're going to keep doing this. But we're never actually going to get there at a. So it doesn't matter if the function's defined there or not. All right, let's look at some graphical examples, and then if we have time, or if I think it's relevant, we can come back to these. So we'll do this one and then take a break, and then we can come back after break and look at a couple more. But as far as how 2.7 shows up on the exam, it's just going to be like these graphical examples. So we have some function f that satisfies the limit as x approaches 2 on that function is 5. So it says determine the largest value of delta satisfying each statement. So I think it's really helpful to at least look at all of this and make sense. What is a in terms of like the limit statement? What is a here in this example? 2. Remember, it's the limit as, if we go back up to the definition, the limit as x approaches a. So the thing x approaches is your a. What's L? 5. That's what your function approaches. And L equals 5. So statement A says that if I'm how many units from what on the x-axis? 2, no.
Delta units from 2.
Yeah, right, delta units from 2 on the x-axis, remember, so there's A again. Then, I'm how many units from what on the y-axis?
Epsilon. We're epsilon units from L.
Yeah, in this case, 2 units from 5 on the y-axis. So they've actually given us the epsilon, right? Remember the statement that involves f of x minus L is less than some number. That number for us in that example is 2. That means our epsilon is given to us as 2.
How do you write epsilon? Just like a backwards 3?
Yeah.
It's just hard for me to see because
Yeah,
it's tiny.
It's kind of like a tiny.
All right. So that's why it's important to kind of fit the structure of the definition into something specific, so we know exactly what we're dealing with. Here's A, here's L, and we're given epsilon as 2. We're trying to find the delta. Notice delta isn't given to us in either part A or B. So I'm just gonna write this here. Part A, we're given epsilon is equal to 2. So notice what doesn't change here. We're always looking at the limit as x approaches 2 on that function equaling 5. Okay, so I'm just going to mark here's our A and here's our L. And for part A, epsilon is 2. So that says we are, let's go back up there and look. We are 2 units from 5 on the y-axis. So I'm just going to go 2 units in both directions from 5 on the y-axis. Here and here. So all of those values, does everybody agree, are 2 units from 5? And so really, we just need to pay attention to the extremes. If I need to be within 2 units of 5 on this function, then how close do I need to be to 2 on the x-axis to ensure that that happens?
2.
Okay. So I know this is like the upper limit kind of thing. So that corresponds to that point on the function. And then I just need to project that down to the x-axis, which puts me here. So the lower bound kind of thing puts me here on the function. Project that down to the x-axis, puts me at 1. So in order for this to happen on this particular linear function, if I need to be within 2 units of 5, how many units away from 2 do I need to be?
1.
Does everybody see that? At most, we can be 1 unit away. So remember, the epsilon corresponds to the distance on the y-axis we are from L. Delta is the distance we are from A on the x-axis. So let me just write this here. This distance from A to the to the boundary, that distance is 1, and also in this direction, that distance is 1.
And that would be delta, right?
And that's delta, yeah. So given epsilon is 2, we're just going to use the graph to find the window along the x-axis that we need to be in. That's all you need to do, is find that delta.
And this is just what it would look like on the exam.
Yep.
We'd be given the graph.
I'll give you a graph. I'll give you the function, or the limit statement. The limit as x approaches 5 on this, x plus 2 is equal to 7. And then it says given epsilon is whatever, find delta. So that'll be it.
can you do delta epsilon stuff without the graph?
Yeah. So like, if you talk to a lot of people that go through Calculus 1, this epsilon delta stuff, as far as like proving, the epsilon delta proofs are probably by far the hardest, one of the hardest things you have to do in calculus. In Calculus 1, anyways. So, fortunately, we don't have to do those. But yeah, you can, the whole idea is that, just like with anything else, we move away from looking at stuff graphically, and we're able to work it out algebraically. So these things are typically done algebraically. I'm gonna move this up. This was part A. Yeah, that'll be. Okay, so part B, what changes?
Or epsilon changes?
Your epsilon changes, and that's it. It's still the same function, still the same limit, still the same A value. So this time in part B, what is epsilon?
1.
Okay, so in part B, we're now given epsilon is equal to 1. I'm going to erase what we have here, because it's going to change slightly. All right, now with epsilon equals to 1, that says I want to be within 1 unit of 5 on the y-axis. So up here or down here, 1 unit from 5, 1 unit from 5 on the y-axis. Again, I have to use the function itself to determine where that puts me on the x-axis, or what that delta is. So just, with something like this, do your best. Looks like it's right in the middle, though. Yeah, so that's like 2.5, and then the lower bound, yeah, it's like it's 1/2. So now how close do I need to be to 2? 0.5. So this is now 0.5 units in this direction, or in this direction.
It's not ever gonna be something like specific where it's like, it's exactly 0.66.
Oh, yeah, probably not. Since we're using a graph, you're gonna have to have specific tick marks there to count.
Do we need to fill it out? Like, do we need to fill out the graph, or is it just more for our help to figure it out? Like, on the test, we don't have to fill in the graphs like you did here?
Yeah, I mean, we don't have to draw these lines.
Right.
If you can just kind of picture, you definitely need to picture that in your head, though. So I would just draw those lines, project down to the x-axis, just so I know for sure I have to be from here to here within this A value. Okay. Just one other thing. Like, what if this were A? And let me look at something specific. What if this were 4? And over here we got an x value of 7. But over here we got an x value of 2. Like, so we're just assuming that whatever the function is, we're projecting down to the function and getting this bound here
It's just not right.
and this bound. So is that wrong?
Yes.
Depends on the function, right?
Yeah.
What would we do in a case like this? What would I say delta is? Would I say delta is 3 units? Or would I say delta is 2 units?
We should say 2.
We should say 2 units. Why?
Does 2 will always be correct, but 3 is only correct half of the time?
Yeah, right. So if I say delta is 3 units, it's fine from the right of 4.
But
if
not
de-
from the left.
Yeah, but not from the left. If I say delta is 3 units, then that's going to put me out here, which is outside of where I need to be.
So say the smaller one.
Yeah, so delta is always the smaller, between an asymmetric interval, delta would always be the smaller one, just so you ensure that you're definitely within that window. Okay, sorry I went a little over, but we'll take a break. Does anyone have any questions before we take a break? All right.
vividly remember. So polynomial function is when the exponent is larger than 1 and a.
Actually, a linear function could be considered a polynomial too. Yeah, constant functions, linear functions, squares, cubed, fourth powers, etc.
Okay.
Yeah, those are all polynomials.
Okay. So if it has a square root, if it has an x, then it's technically smaller.
Yeah, well, it has to be like x to a power.
Okay, that's
And
what.
in combinations of x to powers, right?
Okay, yeah.
Yeah, that's a polynomial.
And then a rational function is like 1 divided by.
Yeah.
Okay. What exactly is a square root function? Does it all have to be an x square root, or does it just have to have a square root in it?
It would have to be like this is the primary square root function, but it could be like this. That's still a square root.
Would it just be like a square root function?
Yeah.
Okay.
Yep.
Yeah.
That is a y.
Yeah,
That makes sense.
yeah, so in the sense of the domain though, like this x to the fourth isn't causing you any restrictions, nor is that 7 or 2. The only restriction comes from here. So I can only plug in 0 and positive numbers into this as a whole function because of that piece right there.
Okay, that
Yeah.
makes more sense.
Okay.
Okay, and then these are all continuous on certain intervals.
They're continuous on their domains.
Oh, okay,
Yeah.
that makes sense. That's all. Very cool. I learned this like 5 years ago. I don't even remember what I had for breakfast this morning. I can just walk around.
Sure.
Just on my elbow.
Yeah. Well, no, it's because that's this when we see f, the absolute value of f of x minus something is less than something. Yeah. That's your epsilon. So whenever it's f of x, the absolute value of f of x minus something less than something on the f of x part, that thing right there is your epsilon. But it just so happened that in this example, our a for the x matched this property.
I just wanted to make sure if I was on the right track. I jumped a little bit ahead.
Okay.
But
Sine is around 11, so I can check right here. Yeah, so you got delta for A.
Scroll down, you can notice
those
values that we were solving.
So exciting.
We had f of x minus L, which is less than 2. Just like I think I haven't figured out like how that actually. It was more.
Okay, for the sake of moving things along, why don't you all try example 10 and example 11. So all you want to do is say what delta has to be for those particular epsilons.
Oh, you have a handout for those functions?
Not an extra one.
Yeah, let me see if I can put that in. That's the best I can do.
Yeah, let's go.
I'm doing 10 and 11.
10 and 11, yeah.
Unless you're just interacting with something.
You might think you just tie one shoe. It might be
Totally fine. Different one. There we go. Yes.
Oh, that's so cute. My phone's not working, but now that you give me these.
No. I have a cute phone too. It's not like that now, but it's
Okay, this is right.
This is like 1/2, so we do
Did you guys not get it? No. Yeah, because it came this way, so I passed it that way. Why did you use that way? Because it came from this way. Yeah.
It went around us.
I figured that people would know kindergarten passing. We can compute the limit, but we can't pass an intended change. Let's be real, half of us can't compute the limit. Speak for yourself, I cannot do differential.
It doesn't really matter.
They did not.
We did not. Thank you.
Just driving absolutely nuts.
Take a nap, you ask help.
So is this over?
Taking me.
I mean, and that's.
Yeah, for this one, one.
Anyone else need this?
Actually,
Anyone else need the attendance sheet?
Well, no, because
I
then we
was
have to
already
look
doing
at
it,
where we're at.
and then-
Sexes, right, so then our window was this one.
What I call this.
How far away was this?
Actually, I guess.
Oh, no. Yeah, see, it just seems like it's so easy.
So when I get a C,
Right, yeah, so many tricks on that. It's like it says where it is so long for the fish to come in.
my new thing is
Oh, right, yeah. Pretty defensive, you know? Yeah, I've heard that in reference to like Zen meditation, like during meditation.
Make
Still be Zen. Yeah, I'm not good at that yet. It's like anything else that takes practice.
Find the smallest possible value, the delta, such that the inequality is true.
maybe I would have passed that
Oh,
test.
is it just one?
To explain how to figure out.
Oh, that's what it means.
Well, no, I already did that.
I thought it meant like get it smaller and smaller, and like you just pretty much say.
No, you said to just plug it in. Plug it in the plug.
I asked if you were
Yeah.
You
all right?
Yep. When you know.
Yeah.
Good. I didn't draw a graph. Love
Yeah, yeah.
I mean, he still doing more.
Did everyone get the roll sheet?
No, it does work. It does. They work. They are just very, they're bad on. It's kind of like that. That's the real thing. But ironically, the real thing is safer. Right. Right, and that's the kind of stuff that like you would create for these other companies, and you would tell them.
When I'm complaining.
And create them, and be like it's worth it. It's not. Right, it's not gonna be. Right, exactly. You'd be the guy that they wouldn't really say it. Oh yeah, we made this product.
All right, I think I made it around to everyone. Everyone had these answers. I'm just gonna do this so we can finish our notes for those of the folks that aren't here. Does anyone have any questions on this? Yeah, right, because then we're just kind of reverse engineering. We know that this is max and min. We see what y value that corresponds to, and then we go over just so we can see what x value that corresponds to.
That'd be 2, I think.
All right, then. Everybody all right with that? All right, I want to run through this last example. Oops. So just to show you how to use that without a graph. Again, a question like this wouldn't be on the exam, but given the limit statement, the limit as x approaches 1 on 8x plus 5 equals 13, let's identify what's a, what's f of x, and what's L. What's A?
1.
A is what x is approaching, 1. F of x is
8x plus 5.
8x plus 5. And L? 13. Is 13. For sure, when you're given the graph, you want to somehow reference A and L because those are the ones that are giving us, those are the ones we relate the distance back to, right? Once we get that window, we have to go back to A in order to determine delta. L, once we have that window, we have to go back to it to determine epsilon. Okay. Let me back up for a moment. Remember, so our definition says that whenever, we'll take example B here. Whenever we're at most half a unit away from 3 on the x-axis, then what happens on the y-axis is that we're 1 unit away from 6. So again, the idea is that we're really working with the x-axis, even though we're working this backwards. And we're saying, all right, well, if I'm within a half a unit of 3, what's y within? Y is within 1 unit from 6. And then if I'm a quarter a unit away from 3, how far away are we from 6? But if we didn't know that 6 was the limit, we would see that, all right, well, if I close in on 3, according to this function, what are the y values closing in on? And then we would say, oh, hey, as I get closer and closer to 3 on this function, it's equaling 6, or it's getting closer and closer to 6. So that's kind of how we were computing limits up until this point, right? It says, what's the limit as x approaches 1 on x plus 1? And we said it's 2. But if we looked at that graphically, we would see that, if I put a smaller and smaller window around 1, then the y values were getting closer and closer to 2. So that's kind of how this works in practice, even though we're looking at it backwards. Yeah. Okay, so then I'll ignore this example, just so we have space to work this. And so now that we've identified these, the f of x, the L, and the A, we're going to say that according to the definition, when 0 is less than the absolute value of x minus A is less than delta. So whenever that happens, the absolute value of f of x minus L is less than epsilon. So once we identified A, f of x, and L, then we just fit those pieces into our absolute value statements. And we're still trying to figure out what delta makes sense here. But we're going to work with the absolute value of f of x minus L. And we're going to try to, our goal is to get the absolute value of f of x minus L to look like the absolute value of x minus 1. And then that way we can relate it back to delta. Okay. So we have the absolute value of 8x minus 8. We'll factor the 8 out. And then, of course, the absolute value of x minus, the absolute value of that product. 8, since 8's always positive, we'll take it out. So that's a good start, because our statement involving x did involve the absolute value of x minus 1. So we took the statement that involved y and f of x and L, and we're able to work it down to where it's some version of the statement involved, the absolute value statement involving x. Okay. But keeping in mind that if this has to be less than epsilon, which means this is less than epsilon, which means this is less than epsilon. So the difference here is we're not given a specific epsilon. In all those graph problems that we looked at, we were given a specific epsilon, so we could give a specific delta. Here we're not given specific things. But I do know that if I divide both sides by 8, now I have that exact statement that was involving x and delta. So what do I need my delta to be in order for this limit to satisfy the definition? Not 1. Not 0 either.
8.
Not 8 either. So here, take this statement. This statement we've whittled down from f of x minus L, right? Everyone agrees with that? So this is what we're looking at. Remember, we have to find the delta. So we're going to take that and say, well, it certainly looks a whole lot like this statement. So if we can, and I'll just write it down here. This is our statement for x based on the definition. What does delta have to be?
1 over 8.
Not 1 over 8.
Epsilon over 8.
Epsilon over 8. Yeah, that's it, right? This was our statement involving x. This is what we've whittled it down to. So these two things have to be the same, right? In order for those inequalities to hold. So all we would say was here, delta has to be epsilon over 8. If all we were trying to find is the delta. So sometimes there's the specific relationship we can come up with. So if I said, all right, well, I want to be within 8 units of my limit on the y-axis, then you would tell me, well, I have to be 8 over 8 units from 1 on the x-axis to make that happen. If I said I wanted to be 4 units away from my limit on the y-axis, then you would say I need to be within 1/2 unit of 1 on the x-axis. So if you look at those other examples that we looked at, the graphs, there is a relationship we can come up with between epsilon and delta. We just didn't come up with that generic relationship. We came up with a specific one because we were given a specific epsilon. And I hope that you see here, if I give you a specific epsilon, that gives us a specific delta. So that's how those work. And honestly, those are and then you go through the whole proof again. Once you found this thing that works, then you go through the whole definition and justify it again. So it's like half of the proof. And we're just going to stop there. But then you can see that this was pretty straightforward. It was a linear function. When you have to deal with maybe even limits that are infinite, or trig functions, stuff like that, these kinds of things get exceedingly difficult. So fortunately, this is it for us. On the exam, it's just a graphing question. Anybody have any questions on 2.7? So I went ahead and wrote out the content for exam 1, just so we don't have to spend another 10 minutes describing what's on the exam. And I will upload this handout or these notes to D2L under exam reviews. So this will be there. I wouldn't worry about copying it down. So every exam I will have some short answer, multiple choice, or true false questions. Many, not all, but the majority of those are more conceptual than they are specific. So just a couple of examples of what a short answer, multiple choice, or a true false could look like are given here. I think that's just one.
It's 1.
Okay, so that's just a particular type of question you could see. It's certainly not all-inclusive. So if that is the case, then what can be said about the limit as x approaches a of f of x?
It doesn't exist.
It doesn't exist. So it's it's there to sort of test your concept knowledge, which is usually a more broader knowledge base than just a specific thing like, hey, I know how to compute a limit. That's great, but it's like really specific.
You also
Okay.
say it's not continuous.
Yeah, we would say it's not continuous at A. That's the best we could say, because if the limit doesn't exist, it can't equal the function value. Okay. There'll be one question dealing with the average rate of change and the instantaneous rate of change. That came from 2.1, where we were given a position function, and it said, compute the average velocity on this time interval, on this time interval, on this time interval, and then use that data to determine or guess what the instantaneous velocity would be. So that's what we did in 2.1 with that. Well, given a graph, you should be able to find the function values and justify where the function is continuous or not continuous by using the continuity checklist. So again, on those, it never said that this function's continuous because it had a hole there. So on the exam, if there's a hole in the graph and you're saying it's not continuous there, don't say this isn't continuous at x equals to 12 because there is a hole. You have to reference the checklist, because then you're referencing the actual definition of continuity in terms of the limit equaling the function value. I know this is really generic, but there are 14 questions about limits to evaluate, and those could cover any limit we've seen at infinity, infinite limits, ones you have to factor, ones you have to use the conjugate, ones you have to simplify using the lowest common denominator. There's trigonometric limits, and we can certainly look at some examples, but I know that's not terribly specific, but there are a lot of limit questions. Given a rational function, you should be able to identify the types of discontinuities and state where they're at. And that's, you can do that through just an algebraic perspective. Okay. Determining the behavior near the vertical asymptote using limits, and determining the horizontal asymptote using limits. And actually, the holes are determined by using limits as well. Okay. One for the intermediate value theorem to determine if we have a solution in a given interval. One limit for determining intervals of continuity on piecewise functions. We had an example like that in 2.6, and then given a function, the graph and epsilon, you should be able to find delta. Really, you should be able to identify something like that. You should be able to identify what we just did. What's A, what's f of x, and what's L. So you'll actually be given like the limit statement and the graph and epsilon. So you have all of that information. So that's what the test consists of. I'll post this as, at least in part, as our review, but does anyone have anything specific they want to look at or talk about? Yeah.
So the practice exam online, do you know how long that is?
I don't. So I do know that it's lengthy. When I give you those exam practice problems, the intent is not to overwhelm you with 100 plus questions.
70 questions or whatever it is.
I'm curious.
So, I don't know, a review might be misleading. There's 49 questions. But the idea is not, hopefully you don't have to do all 49 questions. They're really chunked out in terms of the section. So if you do like the first question and you get it without looking at your notes or needing help at all, then for me personally, I would say, well, I'm good with that concept. I can skip the next 10 questions because they're all similar. If you missed it, then you might say, well, I need to work on this. Let me look at my notes, then try question 2. So there's just chunks of problems that are super similar for those that want to practice more. Some people feel okay with doing a couple and then moving on. Others want more practice. So that's why there's so many questions. It's not that they're all different in the sense of they're all testing different concepts. It's just that a certain concept might be tested, 8 different times before the next one's tested. And again, don't think, don't assume that this review is going to be like the exam. The exams are more like how we word stuff in our notes than how my math lab words stuff. So this is just an extra practice.
So really review the words in the notes,
Yeah.
all the theorems, all the properties, all that.
Yeah, I think that's more. And then of course, once it's really just a practice. That's all it is. You've got to practice certain those skills at some point. If you didn't get enough of it through doing your homework, then those are there as an addition to. Yeah. Yeah. What was your question?
I was wondering if we could go over a limit with trig functions.
Yeah. So that's. So as far as trig functions are concerned, really a couple of things that you should remember. Limits at infinity. On sine and cosine. So what do we say? What do we know, or what can we say about those limits?
They don't exist.
It's in between 1 and -1. So remember, in order for a limit to exist, your function has to approach a specific number. So all we know is that they're in between 1 and -1. As we get further and further out, the functions are still doing this. They never approach anything specific, right? So,
We would use like the space theorem, right?
no, something with like a combination of these at infinity, we would probably use the squeeze theorem. But these limits do not exist.
And that's just even when x is an actual finite number, you would still say that it does not exist.
No. So when x is an actual finite number, for instance, what's the limit as x approaches pi over 4 on sine x, for instance?
Square root of 2 over 2.
Yeah, square root of 2 over 2. So then we get actual values out. But it's only when we look at the limit at infinity on sine and cosine where we get something that doesn't exist, because they never flatten out. Or for that matter, they never grow up to infinity or down, so.
So if it says x approaches 2, it's not.
We know it's going to be something, yeah.
Quick question too.
Yeah.
So basically on this, it's once you put a number in for the limitation, you should be able to get a number out for the
Mhm.
limitation with the trig function, but if you're just going to infinity, it's just going to be does not exist because you're not given a specific
Right.
limitation.
Right, for sine and cosine, yeah.
Okay.
Yeah. To remember the other ones though, those have asymptotes. What about if you were asked to compute the limit as x approaches infinity on cosine of 1 over x?
Wouldn't that just be 1?
Would that be 1? What do y'all think? What is the argument approach as x approaches infinity? 0. So this limit is approaching cosine of 0, which is 1. Let's see if I have another one here. Yeah.
1 divided by infinity, which is the arbitrarily small number.
Right, yep.
Okay.
So 1 over a large number, or any fixed number over a large number is getting smaller and smaller. I don't think I actually wrote any of those other ones down.
So problems with the conjugate, can we solve them by using the lowest common denominator? Or do we have to, if you ask on the exam, use it solving the conjugate, we have to do it with the conjugate?
Yeah, so let's look at that in a minute. But as far as conjugation goes, those typically showed up when we had functions involving roots.
Great.
So if you have to compute a limit that involves a root, and you're not getting it to come out, like if you evaluate it directly and divide by 0 or get something weird, then that's when you should take algebra and say, well, what happens if I multiply by the conjugate? Can I simplify this function to then try to reevaluate the limit? And so the trig functions are a little bit more unique to algebraic functions because there's so many representations, right? I can represent, the cosine of 2x in a couple of different ways. So then it really comes down to, primarily you should definitely know those Pythagorean identities. You should know those for sure. And those double angle, cosine 2x, sine 2x.
We need to illustrate any graphs.
Do what?
We need to illustrate any graphs.
What do you mean? Like graphing stuff?
Yeah.
Um,
So I know on my math lab, you just told us to do Desmos. When I said illustrate the inequality of sine of
Oh, right. No, you won't have to do that. Yeah, so that was in reference to the squeeze theorem where you're trying to show that one function is in between two functions. And it said verify that this inequality is true. Yeah, so you won't have to do that on the exam. So yeah, like if to go back to your question, Omar, let's look at what if we had the limit as x approaches 49, and our function was 49 minus x over 7 minus root x.
We can still use the lowest common denominator here, though, right?
Well, in the sense of like just rewriting this algebraically, yeah, you could. As far as it helping you evaluate that limit, it wouldn't help you.
Okay.
But yeah, you can still involve that. The idea here is, and especially with functions that involve roots in a general sense, usually the conjugate method is the most generic approach. But we did see some of these in this type of form that we could factor. So you could use the conjugate method here to simplify that, or you could factor it. Doesn't matter. Conjugate would be 7 plus root x. Or I could factor 49 minus x as 7 minus root x 7 plus root x. Remember, this type of factorization only applied to those differences of square kind of things. I don't know if this was in 2.3. This was another example we had in our notes from 2.3. Illustrated a limit with a root that we couldn't involve like a factoring type of strategy, where we had to use the conjugate. Okay. Any other specific things? Yeah.
It was a homework question, but I don't understand how I got it. So it was like.
Oh, you want to just read it down?
I was just gonna read it.
Okay, I'll try to translate.
So it was the limit of h approaches 0. It is the square root of 36 plus h. And that minus 6.
All of it?
Yeah, yeah. And
Okay.
all over h. And then I got 1/12, but I don't know how I got that. It's just find the following limit.
Okay, so this fits into what we were just talking about. So this one, we have issues here with h approaching 0 on the bottom, but this is a function that involves a root. So this is where we would multiply the numerator and denominator by the conjugate. So we're going to multiply by the root 36 plus h plus 6 on top and bottom. Remember, the issue here was the h approaching 0 on the bottom, so don't distribute that through the bottom on this other part. We'll just leave that as is. So our denominator will just be all of this stuff. The numerator now is the difference of squares. So we have this thing times this thing. That's our a minus our b, and this is an a plus b. So that's a squared minus b squared. So square root of 36 plus h squared is just 36 plus h. Minus 6 squared is 36, yeah. So then we see what happens up top. The 36 is gone with this one, and then we just divide the h with the h. And so as h approaches 0, what is our limit?
1/12.
1 over 12.
How would I know when to do that versus assume it's an infinite? You know what I'm saying? Because in like the next section, we talk about how as x approaches 0 and 0 is in the denominator, we would assume that the number on top is small divided by, well, not assume, the number on top would be small divided by a very large number, therefore it's infinity.
Okay.
How would I know
Yeah.
when to do that versus just assume it's infinity?
So what happens when h approaches 0? What happens to the numerator as h approaches 0?
Get 0. Oh, okay.
Yeah, so here with this limit, our direct substitution is 0 over 0. And remember, that can have any value, right? If that were, in the sense of like a vertical asymptote, what happens is the numerator approaches something finite, but the denominator is approaching 0. Okay. So when you get like 0 over 0, you know, like, you know, algebra is involved. However, if it's some number over 0, then this is approaching, you know, positive or negative infinity, depending on the sign that you're approaching 0 through.
Right.
Yeah.
Right.
Yeah.
What happened to the plus h and under the square root?
From here to here.
Yeah.
So since it was approaching 0, we just plugged that in.
Oh.
So then we ended up with a function that was continuous at 0. Yeah.
What was the case where like infinity over infinity is 1?
Not always. No.
No, it's not. Like what was the case?
So yeah, let me just write this here. That's we can't determine that. We have other methods needed. Okay. Same thing with infinity over infinity. Other methods are needed for those two. Typically, we did see instances where if we plugged infinity in directly and looked at it sort of symbolically, that situations on like a rational function as x approaches infinity, like 2x squared minus 3x plus 1 over 4x squared plus 6. If we don't look at that in the correct way, we would say, well, if I directly substitute, then I get infinity over infinity, right? But the answer is the limit is actually just 1/2, because limits at infinity mean that all I need to do is look at the leading terms in the numerator and the denominator. So that's a case where infinity over infinity. And then you can see how infinity over infinity could be any value, right? All I have to do is change these numbers. This could be A and this could be B. Infinity over infinity is A over B. You give me an A and a B, and it's always different, right?
What if you have x plus 4 over x?
Yeah, same thing. X plus 4 over x would also be the same thing. So again, the limit is at infinity. All I need to do is look at the leading term in the numerator over the leading term in the denominator. And then it's just 1, right?
And all of these are discussing horizontal asymptotes, right?
Right. In behavior.
What would the horizontal asymptote be at y equals 1?
Y equals 1, yeah. Horizontal asymptote at y equals to 1. This is horizontal asymptote at y equals to 1/2. Is that helpful? Any other things y'all want to talk about?
No one else does, I have to work.
Okay.
There was another question from the homework. It was saying how, analyze the following limits and find the vertical asymptotes, and its f of x equals x minus 6 all over x squared minus 36.
X squared
Minus 36.
minus 36. And what does it want you to do?
And it says, analyze the following limits, and the limit is x approaches 6, and then it has x approaches negative 6 on the left.
Okay. So the idea is like this would be similar to an exam question. It says you're given this rational function. So, you know, what are the discontinuities and what types are they?
I mean, you have
There's
a
a
hole.
hole.
Okay.
And that's equals 6.
Okay.
In some y point, you have to plug it in. But
Yeah. And so we know that there's a hole because this is this, which means that this function is really this.
So there's a vertical asymptote at negative 6.
Okay, so we would say vertical asymptote. Remember, that's an infinite discontinuity. at x equals to -6. And what else?
Why is it -6 and not 6?
Because if I plug 6 in here, it's 1 divided by 12. If I plug -6, then, yeah. And then there's a removable discontinuity.
X equals 6.
Removable discontinuity at x equals to 6. So then when it says identify the behavior of this function near the vertical asymptote, you have where the vertical asymptote is. You've already identified that. So around the vertical asymptote, we would say, all right, what's the limit as x approaches -6 from the right, and as x approaches -6 from the left.
Yep, big click.
And we know our original function is equivalent to that. No matter what limit we compute, we know that this thing will always be this, right? So all we're going to do is compute these limits here to see which one's positive and which one's negative infinity. And then that way we know, like, as we get closer to -6 rather, what is our function doing in terms of, you know, whatever. But yeah, I mean, I'm glad you asked that. I wanted to mention that anyways, so.
I'll say, 'cause I remember some homework as well, and don't you also have to kind of pay attention to the way you're adding the x in there, whether it's on the left side or the right side?
Yeah.
As well as the number that you're going to be adding or subtracting it from, because that might also, in the process, flip the
Right.
sign, whether it's going to be positive or negative.
Right, yeah. And so it's not always sufficient enough just to know that the denominator is approaching 0 through positive or negative values. You have to take in the consideration of the sign of the numerator in consideration as well, because the whole thing contributes to the function, which is a quotient. But these are always positive. So as we approach -6 from the right, what is this approach?
Positive infinity.
That's approaching 1. Yeah, the numerator is approaching 1. The denominator is approaching 0, but through what kind of values?
Very small positive.
Yeah, because that's like a -5.9, -5.99, et cetera, et cetera. So then this limit here would be infinity. Similar thing here, you have 1 over 0, but this time we're approaching 0 through negative values, which makes this a negative infinity. So now we know on the original function, now we know the behavior near the vertical asymptotes, or asymptote rather in this case. Right, as I approach 6 from the left, the function dies off towards negative infinity. So, you know, it's down here as I approach from the left, and positive infinity as I approach from the right. These functions often had horizontal asymptotes, which, as we mentioned just a little bit ago, that involves computing a limit at infinity. And how do we locate the whole? By using limits? No, by factoring, we could say there's a removable discontinuity at 6. What's the ordered pair then for the removable discontinuity?
Why would it be 1 over 12?
Yeah, and the way we get that is,
You just plug 6 into your completely simplified
yeah,
equation.
so our removable, I'm just going to abbreviate that, pretty long word. Our removable discontinuity, our whole, we're just going to compute the limit as, we already said that there was a whole at x equals to 6, so you just compute the limit as x approaches 6 on the function itself. So the whole is at 612.
Why 12? It'd be
112.
Right.
So that's how we would identify the ordered pair for the removable discontinuity. Yeah. I don't know what else we can say in a minute, except for good luck. I'll see y'all on Thursday. Have a great weekend. Let me know. Email me if you have any questions.